number of people would have depended on number. Okay, settle down. I know that was a lot of fun, but you're going to have to settle down. Okay, was that bad? Yeah. So for those of you who did not realize it, the first question was about the simplest possible group you could possibly be given. It has two elements. And you can call this whatever you want to. So there's only one thing you can do to that rectangle that's non-trivial. There's different ways of saying what it is, but there's only one thing you can do. So you have two elements in your group, nothing and that thing. And then you could actually represent it as 1-by-1 matrices if you like. Or you could do a two-dimensional matrix, it doesn't matter. But anyway, the solution, I'll write up the solutions are written up in, hey, shh. I will write up the solutions and post them on the course website if you want to see how they are done. Okay. You guys have got to stop talking, please. All right, so especially on days like this where we only have an hour of class time and we got a lot to get through, we need to get straight on to things. So I'm going to go straight into this without asking if there are any questions, and hopefully maybe I'll address some questions that you might have along the way. So in your homework, in that quiz, you've now derived the number of continuous free parameters for several different examples of groups. And I'll just give you sort of a survey of some general results. So if you have a group SON, then as many of you have already discovered by whatever means you have at your disposal, the number of parameters in that group is 1/2 n times n minus 1. If you have a group, which I'm going to write this in a weird way, of SON minus m comma m, that means that the sum of these two numbers is just n. All right? Then that actually has the same number of parameters. It's a tricky way of me getting to write the same formula twice. If you have a unitary group, UN, then you have n squared parameters, and if you have a special unitary group, you have n squared minus 1. Okay? Those are the general results for unitary and orthogonal groups. And of course, if you're doing physics in different contexts, or especially if you're working in different numbers of dimensions, then a lot of these things actually, these more general results can become important. I find myself working with SO32 rather often, SO16, things like that. But for this course and most of what we're going to talk about, there's really only 4 cases that we are going to be looking at in any detail, so I'll just write down what those are. So for us, we're going to make heavy use of SO1, 3, and Monica is going to tell me how many parameters are in SO1, 3. And you can use the formulas I wrote. 6, good. Okay, so there's 6 parameters in SO1, 3. We're also going to make use of U1. Jacob, how many are in U1? 1, good. Mark, you get SU2? Yeah, you mark.
Okay. SU2 gives you 3.
Good. And Jordan?
SU3 gets 8.
Good. All right. So you guys are awake. That's nice to see. You can do simple arithmetic. That's even nicer to see. Okay. Those are the 4 groups that we're going to mainly use throughout this course. All right? We're going to use them in different ways. We're going to talk a lot about this group today, but this group is essentially the space-time group of space-time transformations in special relativity. Okay? And those 6 parameters, as we've already discussed or mentioned briefly in the end of the last lecture, correspond to the 3 rotations and the 3 boosts. Okay? one free parameter of U1, 3 free parameters of SU2, 8 free parameters of SU3. Anybody know what I'm writing? Those are the force particles in the standard model. So you see why the counting of free parameters is important for these 3 forces, because they actually tell you how many messenger particles you have associated with that force. For every free parameter, you get an additional messenger particle. Right? So we have 8 gluons. I just call them all G. G1, G2, G3, whatever. We'll actually find a better way to label the gluons when we talk about these in more detail. We have 3 bosons for the weak interaction, and we have the 1 photon for the electromagnetic interaction. Okay? So you see how these transformations are already starting to replicate some of the structure that's associated with these forces. Now I want to be a little bit careful here, because this is a little bit of a lie. So in your paper, write sorta. And we'll go over what sorta means a little bit later. People conveniently refer to U1 as electromagnetism and SU2 as the weak interactions, and that's really not the way that it works. It's a little bit more complicated than that for reasons we'll talk about in a few weeks. Now, the way that we actually use these symmetries is going to be very, very different depending on whether we're working with the space-time symmetries versus these internal symmetries. What we're going to use space-time symmetries to do is to limit the form of what we can put in our Lagrangian. So remember, at the end of the day, we've been talking about groups, and groups are really useful for describing transformations. But our ultimate goal is to have symmetries of the Lagrangian. We want to have a Lagrangian such that if we transform it by one of these transformations, it actually looks the same. Okay, and that's a curly L for specific reasons we'll talk about later, as opposed to a regular L. All right? Saying we have symmetry under these space-time transformations is going to tell us what kinds of combinations we should put in here. So for example, you're used to talking about 1/2 mv squared as the kinetic energy of something, okay? Well, this is a term which does not transform well under this group. So this is not going to be allowed in our Lagrangian. We need a better version of a kinetic energy, and we'll figure out what that better version is. Okay? So we're going to use space-time transformations to sort of tell us the forms that things should take. Here, we're going to follow a slightly, so you can kind of think of using the space-time transformations to take all possible things you can imaginably brainstorm and throw a bunch of it out and shrink yourself down to a small set. Here, what we're going to do is we're going to start with one term, and by then saying, I want these things to be symmetries, we're going to generate another term. So we're actually going to grow what we have by forcing these to be symmetries. But what we'll find is that that growth is exactly the introduction of interactions, forces. Okay? So we're going to see these play very different roles, but at the end of the day, the bottom line is symmetry. It's all transformations that you do on things in the Lagrangian, but you want the Lagrangian itself to remain unchanged. Okay? All right. So now, technically speaking, the symmetry group of the standard model is simultaneously all of these. Okay, so if you really wanted to write it as one transformation set, you would call it SO1, 3 cross SU3 cross SU2 cross U1. Now that cross, again, we're not going to worry about the technical details of it, but essentially what this means is that anything that I am going to work with in the standard model, any particle, any field, okay, has to transform in some representation of all four of these. It could be a trivial representation. So to give you an example, if I look at a quark, and I know you don't really know what a quark is yet, and that's okay. What we would find is that under this, it would transform as a spinner, and we'll talk about spinners on Thursday. I haven't talked about spinners yet, but I want to give you the right answer. It's a spinner under this. It's a vector under this. It's a vector under this, and it's a vector under this. Okay. However, if I think about a W plus, actually let's do a Z naught. If I do a Z naught boson, that's actually a vector under SO1, 3. It's a singlet, or a scalar. Well, maybe you're more comfortable with the word scalar. It's a scalar under SU3. It doesn't transform at all. It's actually a weird thing called the adjoint under SU2, and we'll define that word later. And then it is a scalar again under U1. Okay, so every single particle is going to have some representation of all four of those symmetry groups. Yes?
If we're kind of crossing all this together, is there any sort of meaning to like the 18 free variables that we have in the standard model? Because if we just kind of add up all three.
The 18 free parameters in the standard model. So that when I refer to 18 free parameters, that's a different thing. Those are inputs. Those are quantities which we have to determine from experiment. They're not the free parameters of counting group transformations.
Yeah, that's what I was asking, is there like a correlation?
No. Yeah. Okay, so the bottom line is we're going to be considering things which are rather complicated. It's not enough to say that something is a vector in space-time. You've also got to tell me how it transforms under SU3, how it transforms under SU2, and how it transforms under U1. Okay? Which is weird because, right, a lot of times we think of a vector here as a 4-component object, but then if it's also a vector here, that means it's got an additional 3-component vector, and if it's a vector here, it's an additional 2-component vector, and if it's a vector here, it's an additional complex number. So it is simultaneously all four of these things. Okay? Yeah! And if I do an SU3 transformation, this is the only one I touch. Okay? I can do a transformation here and here together, and I'll rotate those two. Okay? And we'll flesh out this structure in detail in due time.
Does that mean if we know, if we don't know what we're working with, and we know it's vector in one of these, is it determining that what it is in the other ones, or are there like?
No. Knowing what it is in one doesn't tell you anything about the others. With the exception of a very complicated story that's tied up with this sort of. Okay, and I mean, I'll just give you a preview. The real way to understand these two groups is through what's called electroweak unification, where the electromagnetic and the weak interactions are unified into a single group. And it's a really frustrating unification, and you'll see why when we talk about it. Okay, so you know, that looks complicated. It's probably way more complicated than anything you talked about before, but it's okay, because that's as bad as it gets. That's it. Okay? These are the groups we'll talk about. So what we're going to do now is spend the rest of today basically exploring SO1, 3. All right? And we will come back in a few weeks and talk about the internal symmetry groups. So SO1, 3 is going to be the relevant set of linear transformations that sort of underlie special relativity. And so I'm going to generically call an element of SO1, 3 lambda. Okay, and the first thing we want to do is sort of explore what do these lambdas look like. Okay, now Josiah is going to remind us what condition the lambdas must satisfy. What is the condition that defines SO1, 3? Yeah.
So for SO1, 3, it's going to be our special orthogonal group. So the determinant is going to have to equal 1, and then we have the P transpose P equals 1. That equals the identity A transpose or lambda.
All right, you need to phone a friend. Peter, help him out. What's wrong with this? You're close. Claudia?
Should be lambda transpose G lambda.
Yeah, there should be actually the G in here. Because remember, the G is actually what makes this not SO4. Okay, where G is minus 1, 1, 1, 1. Okay, we're going to try and work with that convention of minus 1, 1, 1, 1. I realized that the book, if you actually are looking at the particle physics book by Griffiths, it uses 1, minus 1, minus 1, minus 1. And that's because Griffiths is stupid. So, no, he's not stupid. He's a really swell guy. He just does the wrong thing there. Okay, so we talked about that the lambdas essentially are rotations. And I put rotations in parentheses because they're not quite rotations, but one way to sort of organize the lambdas is these six rotations in the 6 different planes that you can construct out of 4 dimensions. So we talked about how it's not really useful to talk about a rotation around the x-axis when you're in 4 dimensions, because that doesn't mean anything. It's more useful to think about a rotation in the xy plane or the yz plane. So we can think of this as rotations in xy, yz, zx, but then also in xt, yt, and zt. Okay? Those rotating in those 3 planes are spatial rotations. Rotating in these 3 planes are what we typically call boosts. Okay, and all I want to do to start with, to kind of get your to get you familiar with the details of the story, is just kind of show you what these things look like. So let's start with some vector. Okay, and a very useful vector is a vector which we build from the coordinates, and so it's going to have essentially infinitesimal displacements along time, x, y, and z, and perhaps Zach would like to tell me why I threw a C in there. Yeah. Why did I throw a C in there? What does a C do for me? Want to phone a friend?
Jordan. I call him Jordan.
Jordan.
Yes. It makes your units kind of work.
Yeah, it just makes the units work out. I mean, if you just had dt here, it would have units of seconds. These would give units of meters. It'd be kind of weird to say those are all components of a vector, but if I say c dt, then this has units of meters. Of course, if we're highfalutin theorists, we'll just set c equal to 1. That's going to natural units, and therefore seconds and meters are the same. I'll try not to do that until we absolutely have to. Okay, so that's what I'll refer to as a coordinate displacement vector. And the first thing I want to do is explore what the lambdas do to this thing. Okay? So a first example is just a good old rotation. Okay, so let's just for example pick an element. Well, actually we'll use lambda yz by an angle theta. So if I want to rotate in the yz plane, I need some matrix which will take this thing, act on it, and give me back the rotated form of that vector. Okay? And probably doesn't take a lot to figure out that you're first of all not doing anything with time if you're just doing a spatial rotation. So the time part of this is going to just be the identity. Also, if you're rotating in the yz plane, you're not doing anything to x. So the x part of it doesn't do anything. And then the only non-trivial part is the stuff in the y and z. And then this, of course, is just cosine theta minus sine theta, cosine theta, where I say this is just of course because this is the form of a 2-dimensional rotation matrix. If you're not familiar with that, go back and review it because it's going to pop up a lot. All right? Now, if you take this lambda and you actually sat down and did the matrix multiplication, you will find that if you transpose it, multiply it by G, and then multiply it by itself again, it gives you back G. And of course, the determinant of this is +1. Okay? So if we call this the Lorentz group, which we often do, the Lorentz group contains spatial rotations. Of course, it contains more, but it does contain spatial rotations. All right. People sometimes leave that detail out. Now, an important part of this story is if we know that one of the things that a spatial rotation does is it leaves the length of a vector invariant. So if you think about it, if I'm rotating in the YZ plane, one of the non-trivial consequences of this is that dy squared plus dz squared is unchanged. I mean, obviously c dt squared is unchanged because nothing's happening to time, and dx squared is unchanged. But what's nice is that even though you're doing something non-trivial to the y and z, this combination is unchanged. And of course, the reason for that is the trig identity that these satisfy. That sine squared plus cosine squared is equal to 1 for any angle. Okay, so the invariance of the sum of the squares relies on the use of sine and cosine and that identity. Yes?
At first I thought that these were just constants. Are they actually differentials?
Yeah, sorry, these are coordinate differentials. Okay. So for those in GR, so for those who took GR, let me see if this. Oh, look at that! Michael used this. It's convenient because he took GR. Why would I not consider just a position vector? This is a hard one. I'm not going to lie. This is really hard. How do you define a position vector, by the way?
Oh.
The position vector has its own, like, you're using the coordinate system for it, whereas differentials are not.
Well, no, the differentials are using the coordinate system. Peter, you want to?
ds is invariant regardless of the coordinates you choose?
No. This is the one vector which, when I start doing sophisticated stuff, I should never actually consider.
It defines inversion?
It's what's closely related to that. How do we define a position vector by writing down a coordinate system and then taking the coordinates of a point and then drawing a line from the origin to that point? What's wrong with that?
Straight line. It's not a single point.
It's not defined at a point. So one of the things that we learn when you do a sophisticated treatment of vectors is that vectors don't live in a space. They actually live in the tangent space. This is why this idea of creating vectors as lines between points is not a good one. You have to actually have your vectors living in the tangent space to a space, and that's defined at each point. So you can talk about the tangent infinitesimal displacement vector, but you can't talk about a general position vector in a curved space. But anyway, that was a challenge question for the GR people. Clearly they forgot, but it's okay.
Isn't that sophist's question?
We won't have to concern ourselves with tangent spaces in this class, so don't worry about it. Anyway, so yes, but those are coordinate differentials. Okay. All right. Yeah. Any other questions about this example? Because now we're going to move to the non-trivial one. Okay. So the second example is if we want to do, say, a rotation in the, I'm going to call this the xt plane. Okay, and before I write down what I'm going to write down, let's make an observation. Oh, I didn't actually write down the. I didn't write down the invariant. Okay, so I guess we'll skip ahead and we'll go ahead and write this down to motivate this. So can anybody tell me if I take that coordinate vector, Marie's not here, is she?
No.
Slacker. Robin,
Yeah.
what would the dual vector look like? What would the dual representation, if you will, look like? So I can think of this as a representation of this guy, or a representation of the Lorentz transformations. What would the dual look like?
No.
Okay, don't worry about it. The order of presenting this is not going to be convenient, but I'll come back to it in a second. So essentially, if I'm doing transformations that include time, instead of something like this needing to be invariant, it actually is going to be something like this that needs to be invariant. So I'll explain why in a few minutes. But essentially, here we're just adding the squares. But when we include time, there's going to be a minus sign that comes in. Now, if you just look at the form of that, to keep this unchanged, it's clearly not going to work to use sine and cosine, right? Anybody on board with that? Sine and cosine don't satisfy an identity that has a negative in it. But what does? Sinh and cosh, exactly. So if we instead, that's okay, if you don't remember that. I halfway remember it. I always have to go back and look at which one has the negative in front of it. But sinh and cosh actually obey an identity that minus sinh squared plus cosh squared equals 1. So that means if we write down a matrix that is going to preserve something like this, then instead of using sines and cosines in it, we're going to use sinches and coshes. Okay? Now we can do that, but it's not very intuitive what you get. It does have one interesting aspect to it. If I have sine theta and cosine theta in my matrix, what can you tell me about the number of different transformations this corresponds to, or the compactness versus the non-compactness of the set of transformations? Is it compact or non-compact? It's compact because the angle theta only takes values from 0 to 2 pi. However, if I'm now working with sinh and cosh, is that compact or non-compact? It's non-compact. So the boosts are actually going to be non-compact transformations. Therefore, overall, you would call this a non-compact group. If it's got some non-compact transformations, it's a non-compact group. Okay? Now, I am not going to write down the matrix in terms of sinh and cosh. Instead, I'm going to write it in a more familiar form. You can, if you want, look in text, come and talk to me, and I can show you how to derive this more conventional form from the sinh and cosh. All right? But this is definitely going to be more identifiable to you. So in terms of a parameter beta, which is just V over C, this matrix is going to be gamma minus beta gamma minus beta gamma, gamma 1, 1 with zeros everywhere else. And here I'm defining gamma as 1 over the square root of 1 minus beta squared. Okay? So if you've ever seen a smidgen of special relativity, these are things that you've certainly come across. The famous gamma factor in the Lorentz transformations. Okay, so before we try and give this an interpretation, mind you, it will satisfy those two conditions. And you can prove that. All right, you can now take this matrix, transpose it, multiply it by G, multiply it by itself. Using the relationship between these two, you get some nice cancellations, and sure enough, you'll just pop right back out, minus 1, 1, 1, 1. Okay? But now what I want to do is give this thing an interpretation. It's kind of a rotation in the xt plane, but it's already not quite a rotation because it's got sinches and coshes instead of sines and cosines. So let's see if we can make this a little bit more familiar. All right, so to get a sort of a physical picture of what that transformation corresponds to, we can do the following. So consider the spatial origin in a frame S. Now, here I'm bringing in some words that you've probably heard before in the context of special relativity, but I want to go ahead and sort of remove any cloud of weirdness from it. When I use the word frame and I say S and S prime, I'm literally talking about different coordinate systems. Every frame has its own coordinates. And if I change from frame S to frame S prime, it is nothing more than a coordinate transformation. These are coordinate transformations. They're taking these coordinates and they're changing them to new ones, okay? So if I consider the spatial origin in a frame S, what I have in mind is that I'm going to consider zero displacements in X, Y, and Z, and I'm going to allow it to evolve in time, okay, because the spatial origin can exist in time, all right, even though you stay at the origin spatially, okay? So what I want to do is I want to transform this thing. So the vector that I'm considering is c dt 0, 0, 0. And what I want to do, so this is the frame S, and what I want to do is I want to see what that lambda xt transformation does to this. Actually, I'll just write in the matrix itself. So gamma minus gamma beta, gamma 1, 1 on c dt dx dy dz. And Hayden,
Yes.
what do I get?
Well, you get c dt gamma minus gamma beta dx. And c negative c dt gamma beta.
Oh shoot, sorry. You guys have to. I made your job harder than it needed to be.
That's okay now. There we go. Zeros.
Gamma beta. You're missing the gamma beta in the second.
Yeah.
So-
There needs to be a gamma beta.
All right, everybody on board? Okay, now the trick is that this is a new frame, S prime. That means that whatever I get, I should interpret as the new coordinates in S prime, which means I should interpret this as a c dt prime. I should interpret the second thing as a dx prime, a dy prime, and a dz prime. Okay? But now I can actually go and match one item at a time and say, what am I looking at? Well, the dy prime is 0, dz prime is 0. What I find is dx prime is minus gamma beta c dt, and dt prime, c dt prime, is c dt gamma. Okay? Now, if I look at this guy, c dt gamma is c dt gamma. Everybody see that? So I could just write this as minus beta c dt prime. Everybody see? That's just algebra. I literally am taking c dt and gamma here, which is the same down here, and I'm replacing it with c dt prime. But now I can rearrange this to say dx prime dt prime is what's beta times c? Brandon. What is beta times c?
No, it should be.
It's just v. Okay, now that might not mean much to you, but let me show you what it means to me. If I have the frame S, and I want to draw this in the right order, yeah. And then I have the frame S prime, and the frame S prime is moving with a speed v along the x-axis. Then the origin of the S frame as seen from the, yes?
Are your coordinates, like your S frame is using T prime?
Oh, sorry, this should be S. Make sure my coordinates are right. Yeah, okay. So if I'm in the, my prime's there. The origin in S, that's what I started with, okay? The origin of this frame, in terms of these coordinates, appears to be moving along the x-axis with a speed minus v. Of course, to get that, this frame would be moving to the right with a speed v. Okay, so if the corner of the room is the origin, and we're all at rest in the room, that thing's at rest. But if I'm moving this way with a speed v, I look back and the origin's moving that way with a speed in the opposite direction, the same magnitude. Okay, so this is how we interpret these things as a boost along the x. Okay. Yeah.
So that's essentially putting us into a reference frame that's moving from a reference frame to the rest, or just changing us.
It is changing us. So I wouldn't necessarily ever say that a reference frame is moving or not, because that only means something with respect to something else. I am, however, focusing on a particular point, and in one reference frame that point is at rest, and in the other one it's moving. So for example, I could stick a particle there and say in frame S it's at rest, but in frame S prime that particle would be moving. And it would be moving along the x-axis with a speed v, along the negative x-axis with a speed v. Okay. So one thing about relativity is that it means nothing to say this thing is moving. It's this thing is moving with respect to something else. Okay. How many of you have seen an argument somewhat like that at some point? Okay. Any other questions about this? Okay, so in the same sense that you can get the other spatial rotations by moving the sine and cosine into other elements. So if I use, a sine and a cosine here, 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 and here, that would be a rotation around the y-axis. And then if I did my sine and cosine here, that would be a rotation on the z-axis. So the rotation matrices all look very similar. You're just kind of moving where your sines and cosines are. Very similarly, the boost matrices, you're just going to be moving, you're always going to have a gamma there, and then you're going to move the off diagonal and the second diagonal to whatever other axis you want to boost along. Okay? All right. Now the wonderful thing is, once you have the 3 boost matrices and the 3 rotation matrices, you've got it all. Because you can do any other weird, complicated transformation just by compounding these things. So that's the beauty of counting to free parameters. Once you've got a transformation associated with one of those parameters, or once you've got one associated with each of them, you've basically got the set of transformations. Of course, it's an infinite set because there's an infinite number of betas you can choose, and there's an infinite number of thetas you can choose. They're continuous variables. Continuous parameters. All right, so, God, the time slips away so quickly. All right, so now let's go back to what I was challenging Robin with, but maybe a little preemptively, and that is, given all of this information, that we have SO1, 3, that's somehow special relativity, what can we do in terms of building an invariant? So, recall that an invariant will be provided by the transpose of a dual combined with an element of the original representation. If I build my dual from an element of the original representation by applying G, where G is the metric. Okay. So this was all information we talked about, I think, either last time or the time before. Okay, so at this point I'm going to adopt some notation, which is just, it's the standard notation from relativity. So what we're going to do is we're going to say an element of the representation R, that's the original vector representation we're dealing with, I'm going to call it V mu. Okay, where mu goes from 0 to 3. And this indexing is that this is time. We call it 0. We don't like to go 1, 2, 3, 4. Can't count that high, theorists. So this is time, x, y, z. That way the x, y, z are the same things you always thought of. So this is a 4-component object. It's got a time piece, an x piece, a y piece, and a z piece. Okay? So now what I want to do, and I'm also going to call an element of the dual with a lower index, v sub mu. And again, mu runs over 0, 1, 2, 3, 4. And then, as an example of exactly what these look like, if I give you a vector v mu, say it has components v0, v1, v2, v3, then we can find the dual v mu by applying the metric and you'll notice that in this particularly simple case, all that the dualization does is it reverses the sign of the first component. Okay? This is a particularly simple space. In curved spaces, it's not nearly as pretty. Okay? But for special relativity, all that it does is it changes the sign here. Okay? It's not as simple as Euclidean space, because in Euclidean space, what's the metric? It's the identity. It doesn't do anything. The dual looks just like the original vector. But in special relativity, our dual vectors have slightly different components. And now, of course, we can take our dual vector and we can form an invariant by transposing this thing and then combining it with the original vector. So if I write that out, I have minus v0, v1, v2, v3, v0, v1, v2, v3, and then you use matrix multiplication.
If that's true, then shouldn't the dual vector be a row?
No, because remember I have to transpose the dual to form the invariant.
Oh, I see.
So I'm being trying to force this into matrix language is a little bit awkward. So you're going to multiply these things together, so you have to transpose it. That's the thing to remember. I'm about to just completely abandon that in a way that I think some of you are predicting. Okay. Now, this thing is invariant. It's very, very important for you to realize that if I had instead constructed this, that would not be invariant. I know it seems very close. It's just a minus sign in the first term. But this is invariant under Lorentz transformations and rotations. This is not invariant. This is actually invariant under the rotational part, but it's definitely not invariant under the boosts. Okay? So now we can go back, and if we take this guy, then we can form what is essentially, we can call this dx mu. It's a better way to say it. We can form dx mu, and we find minus c squared dt squared plus dx squared plus dy squared plus dz squared. And that is the characteristic interval, invariant interval that describes special relativity. So this is the kind of thing I was trying to beat out of Robin before really justifiably expecting him to get to it. Okay? But again, you see the presence of the minus dt squared plus dx squared, for example, that you have to preserve under boosts. So I'm going to now throw something at you which is going to confuse the crap out of you. But I just want you to be aware when you see things, what it is you're seeing, because I've introduced this idea of upper indices and lower indices, and they mean very different things. So for example, this is equal to this. I know. I know. All right. These are the components of the dual vector. That's just the labels. These are the components of the dual vector written in terms of the components of the original vector you started with. All right. So another way to say this, and you're going to go, oh, what's it right there? That the zero component of the dual vector is minus the zero component of the original vector, and then all the other ones are the same. Okay? So just notationally, you got to be careful whether you're putting labels up or down, because they mean different things. All right? In the case of dual vectors, we're almost always going to transpose them, so that's one way to remember. Okay? But we are very quickly, though, going to have to forgo matrix manipulations, because it's just going to get too cumbersome and it can't handle everything. So we're going to end up having to make use of the Einstein summation convention. And for those of you who've seen it, this is comfort zone. For those of you who haven't, welcome to the world of summation. But the Einstein summation convention basically says anytime I see two repeated indices, unless you're told otherwise, you should assume that these are summed. Over all their values. So if I see a mu and another mu, I put in 0, and then I put in 1, put in 2, put in 3, and I add them together. And you might say, wait a minute, Flournoy! Wait a minute! Wait a minute! Wait a minute! Is there a contradiction there?
No.
No, because this is a lower 0. If I put in the components, this becomes minus v0 squared plus v1 squared plus, okay? So the summation is really just add. Don't stick a minus in there. You literally just add. And then the minus comes in when you say, okay, this has a lower index, and I have to remember what that is. All right? Don't worry, if this is a little intimidating, you're going to get very comfortable with it in your homework. Yeah, I know. Okay, so at this point, we've introduced some interesting objects, and now we can actually catalog some of the things that we've encountered. So a vector, v mu, you can define actually as something which transforms under a Lorentz transformation. So I'll write it like this, v mu prime. So if I take a vector in one coordinate system and I change to a new coordinate system, that vector can be written in terms of the old vector by a Lorentz transformation, which I can write like that. So this is just a label for the matrix, okay, that enacts the Lorentz transformations for me. So it's got two indices. It's a matrix, a square matrix. You would expect it to have two labels. All right. One of them should be primed, and one of them should be unprimed, because that matrix carries you from an old coordinate system to a new one. It's the only kind of object that mixes primed and unprimed indices. Yeah.
Why did the index of the vector change?
I could call it mu. That's fine.
Okay.
Yeah, that's fine. Bear in mind, this is not repeated. These are different indices. So mu and mu prime are different indices. Okay. I have now also introduced dual vectors, where dual vectors also transform in a very specific way. Okay. And remember the transformation of a dual vector, if I write it down. So first of all, I'm just going to call it by mu prime. And what's important is that this thing is related to this by this relationship. So, no, wait. So this looks complicated, but remember way back when I introduced duals, and I said if the vector transforms according to that, then the dual vector has to transform according to lambda inverse transpose R. Okay. Or sorry, R total. Okay, so it's just reflecting the exact same thing I said originally when I talked about how duals have to transform. Okay. Now, this will allow us to introduce more general things, so I can introduce a simpler object called a scalar. How does a scalar transform?
By being itself.
Yeah, you don't do anything. It's invariant. Okay. This is an example of what we call a 1-0 tensor. This is an example of what we call a 0-1 tensor. This is what we call a 0-0 tensor. And now it's maybe a little obvious that you can just generalize this. So for example, I could write down a 0 or a 2-0 tensor. And that would be something that has two upper indices. And then if I want to know how to transform it, the beautiful thing about tensors is each index gets its own transformation. So if I transform this to a new coordinate system, I just write down a lambda for each of these. So I write down a lambda, mu prime, mu, lambda, nu prime, nu. Okay. And then I can consider more interesting things. A 1-1 tensor. I can give a tensor one upper and one lower index. All right? And you can build all kind of weird things out of it. Now, as you start looking at these more and more complicated objects, unfortunately, matrix multiplication becomes unusable. So for example, I could give you a rank 3 tensor. Can't represent that by a square matrix. You could represent it by a square cube and do cubic matrix multiplication. I find that a little tricky. But fortunately, the Einstein summation convention gives you the right answer every time. And it doesn't matter how many indices you have. Okay? In this class, the most complicated tensor that we're going to have to work with is a 0-2 tensor. So we will work with a 0-2 tensor. All right? Okay, so in our last 5 minutes, I think I'm going to finish on the following.
What are you saying?
Okay, so here's some sort of meta words. When you start doing special relativity, remember that the symmetry group, or the group of transformations you want to be working with, is SO1, 3. That means that every single quantity going into your Lagrangian has to be have a well-defined representation of SO1, 3. All right? Now, off the cuff, what that means is if I start with something like a velocity vector, which has 3 components, that is not going to cut it, because these are 4x4 matrices. So somehow everything has to be generalized to have 4 components. All right? And the love of special relativity really just comes from finding the appropriate generalizations of the familiar 3-dimensional quantities. Okay? And it's not as simple as just picking some arbitrary thing to throw in that first slot. You've got to pick the right thing, because remember, you have to transform correctly under these transformations to call it a vector. It has to follow that transformation rule, that if it's a vector and I transform, it better transform like this. And that puts a constraint on things. All right? Now, we're going to talk about how you generalize velocity to 4 velocity, and that will also then tell us how to generalize momentum to 4 momentum, and that will lead us invariably to this famous E equals mc squared relationship that people get so hot and bothered about. Okay? But for the final few moments of today, I'm actually going to look at a slightly different example, and that is, remember, every single vector in your theory has to be generalized to something that's well defined under this. Every vector, including things like that. Okay? Now you might say, what in the hell are you going to do with that? Well, you've actually got 2 choices. Okay? So this has got 3 components, and this has got 3 components. So I could try and make this 4 components. I have no idea what that other component would be. And I could try and make this 4 components and just make it 2 4-component vectors. But actually, what we do with it is we instead make it a 0-2 tensor. Okay? So we don't actually have to add a new piece of information. We don't have to come up with, what's this 4th thing that's going to float around? I have no idea what it is. No, we can actually work with the 9 components of these 2 things, but we put them into an anti-symmetric matrix. Notice, if you flip it along the diagonal, it becomes minus itself. And the cool thing is this is really a 0-2 tensor. That is, if you transform it, it transforms the way that you would expect. But there's another way to do it. Okay? And all of this is going to come back, so I'm showing it to you for a very specific reason. There's actually a different way to do it, and that is to remember that the electric field can be written in terms of a scalar potential plus the time derivative of a vector potential, and the magnetic field can be written as the curl of the vector potential, where the vector potential has 3 components, and the scalar potential is just a scalar. Well, guess what? That's 3 things and 1 thing. Why don't I combine them into a 4-component vector potential? So if I'm talking about the potentials in electromagnetism, the electromagnetic vector potential and the scalar potential, now I kind of have a natural candidate for making something that's 4 components. Okay? And you might say, well, wait a minute, do you take E and B and make them this? Or do you take the potentials and make them this? And the answer is it doesn't matter, because this guy, if I work with this potential, is just that. Okay? So let's see that that's the case. If I look at the 0, 1 component, this is d0a1 minus d1a0. This is the derivative with respect to time of the x component. So this is 1 over c, partial ax, partial t. And this is the x derivative of the time length of the scalar potential. Okay? But F01, so this is, if you want to think of this as a matrix, the first label is the row, the second label is the column. I start in the 0 row, and I go to the 1 column. That's minus EX. Which is close to what I want. Hold on, let me. Oh, sorry, I got my apologies. There should be some negatives in there. There we go. All right. And then you can fill out the rest of these terms as well. And you'll find that you actually end up generating the vector cross product, which gives you the magnetic field components, etc. Yeah, it's going to be homework. Okay, so I'm going to give you a problem associated with this in your homework. Work it out. Become comfortable with this because this is going to come back. It'll be a very important part of the standard model. And clearly electromagnetism is part of the standard model, but this particular example we will work through in detail.
Good question. Yeah. Can you remind me why that format matrix is 0 what is that notation again? I thought you could sell it.
Right. This means how many upper indices it has. Lower indices. It has 2 lower indices.
Oh, okay.
So
it would not be the dimension of the matrix, it's 2 dimensional. And that's that was 3.
Well, I can conveniently write this one as a matrix, but generally, don't worry about that. So that's the weird thing. I can write that. So I can write that as a matrix.
You'll get to there and be like, oh wow, this is so easy.
Because they all have 2 indices.
Okay. Oh, okay, I see. So the
but as tensors, they're very different things. That's why just writing something as a matrix doesn't necessarily tell you everything you need to know.
Okay. So what's the distinction here then?
You would have to label it and then write the matrix. Right? If I were constructing this tensor, I can still write it as a matrix. And I can write this as a matrix, but if I wanted to transform that, I would have to use 2 very different transformations because the transformation of lower indices is different than upper indices. So when you write it as a matrix, you have to label what it is that you're working with. This encodes the transformation. Just saying this is a matrix doesn't tell you how it transforms. You've got to know is it transforming with upper or lower indices.
Okay, great.
I'll give you homework.
Great, thanks.
Got a fan? If you want to use it, I'm just going to leave it there. It's actually pulled it from Meyer, which is knocked down. So.
Yeah, this room really is just absurd.